Dear students, welcome to the knowledge series. Here we are going to discuss the continuations of neural network in the area of artificial neural network. You have gone through the previous video series where we have discussed about artificial neural network basic, that is a neural network and its brain structure. For your understanding, neural means that which is related to the nerves or the nervous systems or the neurons, and the network is nothing but a group of interlinked systems, and artificial is something that is produced by human rather naturally. So we use the term artificial neural network, the three words. That is one of the main tools used for the machine learning. And in the neural network, it has three layers that we have discussed earlier. In the neural network, if you try to see this figure over here, this is a root-like structures where we are having on these sides, this is nothing but your synapse or the cell body, where the soma is the central parts, and several nerves or the cell membranes, that is neurons, is the one that pass the signals, that is impulse signals from the previous cells to the current cell, and thereby the action potentials pass through the axon, that it propel or it tries to speed up the impulse through its structures. Thereby the signal will reach to the squares like notations that is being shown over here, that is a synapse, where the post-synaptic actions takes place, and thereby the next cell will receives the signals. And you have to remember that these post-synaptic signals, it takes so fast that that within a small instant you can see the signals pass through several millions of neurons. So that is how this particular action is being represented in terms of the figure, which you can see that this is artificial neuron. Now here in this neural network, in the artificial neural network, I can put it as it is basically an efficient computing systems, basically just like an analogy to the biological neural network. And in the ANN, what we do is that we represent a large collections of nodes, and that's how, if you try to look across the components of the neural networks, there you are having inputs and outputs. Some arrow is being shown over here with a word term W1, W2, W. These are nothing but weights, and there is a bias, and there is a threshold is being shown over here, and inside that threshold there is an activation or a transfer function or a squash function is being used. So the input is coming over here, and individual weight is which is being shown over here. It may be same or it may be different. All these things we'll be seeing in the different form of artificial neural network architectures. Now the representation x1, x2, xn is nothing but the input, and y is the output. W1, W2, Wn is the weight. B is termed as a bias, and theta is the RSI, which has been shown over here. We can take this one into consideration, that this box is further divided into two parts. One is a theta, that is a threshold, and the psi is nothing but an activation functions. So that's how we can take this one into considerations, that is activation functions. So now in this figure, before we go to the further descriptions about this particular figure, let us see this one, this interconnected unit related to the nodes which which is we have shown, or the analogy of a biological neurons are simply to process in the form in the parallel forms. So every neurons every nodes is being connected with the other neurons or other nodes. So this is known as the connecting links, and each connected links is having its own weight, and that weight is that carries the informations, and that informations, if it can able to sum up, and finally if it can able to overcome this post-synaptic or the activation function, then it can propel to the next output through the output Y in. So that how the input signal X in is being transferred to the Y in structures. Now here the neuron internal parts, just like an analogy forms, here we are going to discuss the different components. So let us see the components, what exactly each components represents. Now what is the output? Output is all the combination of the input that has been passed through the several sections, and that's how the section is summing sections and the activation functions. After passing through the summing and activation function, the output is being generated. Now here if you try to see that there is a term like a weight. Now what exactly this weight is in there? Now as I have stated that the weight is the one which contains the information about the signals, and this information is being used as an individual input to solve the problem, or you can say that to pass on to the next neuron. That's how we can take it. If you take it as an example, say for example a child want to learn A, B, C, D. So if the child is initially being taught as A, the child may not able to remember or able to recall what that particular term is being stated by the teacher. But when we do a repeated, when the teacher repeatedly keep on teaching that child about that alphabet, after a while the child will able to catch up. Thereby the child will able to say itself by showing the particular alphabet by the teacher to the child. Now here what we understand is that initially the child was not able to receive that particular signal from the teachers, but later on the child can able to understand what the teacher mean to say, talk about that particular A. So that once the child able to recognize that okay, this A is representing a particular alphabet, that is how that change which has been occurred in the child is because of the change in the weight. So that is what we mean to say. So here the weight contains the information about the signal, and this information is being used by the individual input to solve the any particular problems depending on the application. And weight, it increases the steepness of the activation functions. That means if the weight is sufficiently high, means if it is able to cross the activation functions demand, then only the output will generate. So that is what we talked about the weight. Now next comes the bias. Bias is almost, if you see, it is just like a weight, but it is an independent component or independent variable. So bias has an effect on, bias we can say that it's another components, or it has an effect to increase or it can able to decrease the input depending whether the bias we consider as a positive or a negative. Now what exactly the bias does is that bias basically it delays the trigger of the activation functions. That means if this signal want to trigger here, if that signal triggering time, if it has to increase or decrease, that is handled by the bias. So that is the bias delays the increase and decrease. So if you say a positive bias, so it increases the net input of the network, and if it is a negative bias, it decreases the net input of the network. So that is what exactly the bias means. Now what exactly the bias will do? The bias is the independent component, as I shared to you. That bias will when you try to sum up, bias is going to add along with the total sum of the this input and its weight. So that is what I mean to say. Now let's see the threshold. What exactly the threshold means? Now threshold basically is the final or the post-synaptic situations. So in the post-synaptic situations, what you know, in this one, the value based upon the given input which is being generated at this particular point is being passed to the output. So here the threshold functions, a value is there, that value is being compared, and if that compared with whom, the activation functions. So in the activation functions, this y in will check out if that particular condition is above or below, and if it is above or below, based on that the corresponding output is being generated. Now here let us see the representation in a mathematical forms. So now here whenever we try to see the sum is nothing but the input and its weight. So x1 to x1 into w1 plus x2 into w2 up to xm into wm. So that's how we can put all these particular components. Now here we can put y in dash, that is x1 to xm. Now here I put it as n. This is with respect to the previous figure. I changed the figure. That's why you consider this one as m. So I is equal to 1 to m. So x1 to xm we are taking into consideration for each value of I, because all the I ranges from 1 to m for both x and w. So that's how we get this value, followed by our bias. I have notation bk or b, whichever you can consider. So b is the bias. So this is how we get at the y in dash. So that is what I put it as a y in dash here. Now these functions y in dash is ready here, but whether this y in dash is sufficient to trigger the output or not, that depend upon the activation functions. So here you try to see this particular see the activation functions. Actually what exactly it is that it basically defines the output of the node for a given input or a set of input. Now activation function basically decides whether the neuron is activated or not at this point. When they take into y index, at this point the neuron is activated or not, and if it is activated or not, how the output will judge based on the weight. So based on the weight and based on the bias, with these components, bias and weights, if it is activated, then it is going to produce the output. Now here when we talk about activation function, you have to remember that it can be a linear or it can be a non-linear. So let us not take into consideration linear, non-linear at this particular moment. You take it that as a linear function. So output will be related to the input. So here if you try to see this one, what is the net here? The net is sum is nothing but y in dash. Now this theta or a phi, we take it as the third component for a linear or a non-linear activation functions. So here even if it is a term non-linear, don't worry about this one. We this is the initial understanding. So you just think that it is an activation function. Now what is the output? Output that is the f net, that is the function of this net. If it is greater than our phi, that means this net is greater than the threshold value or the activation functions. It will check that function f of net is greater than theta, then that is considered as the, let us take it as a high or 1. If it is less than equal to 5, then we consider as 0. So that is how. So if anything is generating under that particular condition, if these two condition is generated, if this is greater than, if this 5, then it is producing 1. But if this is less than equal to this, then it is producing 0. So that you get two value, 1 or 0. Based on this, if you try to plot it, you will see that this is the input. Input is what? This one. What is output? Output is this one based on the condition. If your phi is here in the at the input point, if the input y in dash, that is sigma y in dash or sigma net, if it is greater than 5, it is going to produce 1. If it is less than 5, it is going to produce 0. So this is what we see in this case of the component of a artificial neural network. This is one of the very important area which normally appears in all the almost all the university exam across the country. So that is how you should take it into considerations. Now I have put another figure here for your understanding is this one. Now here the same thing I have put down here. Now if you try to see this one, what is our sigma here coming? Sigma is all the x1 to xm, w1 to wm, that is I is equal to 1 to m, w1 x1. We got it here. And what is bias? Bias is nothing but this b. That is what we have told. So bias is the independent component, and these components, the sum components is been put together. The summing will become summing and bias. This is weight, this is input, very clearly is being shown. Now here comes the the neuron firing is taking place, because the function of the net input is being passed to the activation functions, is being passed to the activation functions or the transfer functions or the squash functions. Now here the neuron firing, how it is take place, the output is depend upon the function of net input, that is f of x. You try to see this f of x. So here either f you put it as f of x or f of net, whichever terms you can say. So this is the activation point. So it is equal to 1 or 0 if sigma of this one is greater than equal to 0. You see, if this is greater than equal to theta, not 0, theta. So this is not, this is a theta. So if it is greater than theta, it is 1. If it is less than theta, less than equal to theta, equal to 0, whichever way. So that is known as your y cap. So that is the output. So this is known as y your activation function. Now here 1, what is 1? It is excitatory, and 0, it is inhibitory. That is, you have to keep it in your mind. If it is excitatory and this is inhibitory. And which type of activation function it is? This one. This is a linear activation functions. So this is for your understanding. This is the model of a neuron, and later on we will be studying this perception network, that how it is. But this is the model of a neuron. You just keep it in your mind. Once it appears, you have to draw these figures, and you have to write in these particular forms. So that will completes your model and its mathematical derivations. Now we go to the other segments on the activation functions. We talk about the activation functions. We talk about this one. So we'll talk about, see this particular activation functions. What exactly this activation function, how it is being shown in a different forms. Now you have to understand that the activation functions, this is one of the important questions which is appears in the university exams. Now here the activation functions, it's a functions, basically it performs the mathematical operations. This terms activation function is basically perform the mathematical operations on the input signal. Such functions basically is associated with the for the input to process, thereby the output can able to generate. Now further, the activation functions can be a linear functions or a non-linear functions to produce the output. And normally the linear activation functions, it is being obtained using a single layer network. Single layer means, you have seen my previous video, is that you need only one layer, input layer and the output layer. But when you talk about a non-linear functions and that conditions, in that condition you have to go for a middle layers or a hidden layers into considerations. So non-linear functions are basically widely used for a multi-layer networks. So let's see the activation functions. Now there are different types I'm going to show over here. So let's start with the first, that is a linear functions. Now what is a linear functions? I have mentioned over here, it is a linear functions that means for a given input x, you have to produce a y, which is represented in terms of f of x, that is equal to x for all values of x. That means you are between x and y, you are having a linear line. The slope is passing through an origin, and it is a linear with respect to this both x and f of x. So at every point of x, you are going to get a y or f of x. So y is equal to f of x. So f of x is related to the x, every point of x. So if x is equal to 1, your f of x is going to become 1 if both are same, because both are at every point you are getting the same point, where your linearity will be there. This is 45, 45, so that is how you represent in terms of a degree. Now let's go to the next is a bilinear binary step functions. Now when we talk about a binary step functions, this can be termed as a threshold functions or a step functions or a hard limit functions or a heaviside functions, like that. Several terms being used, and you can refer the books also, you can find these type of terms. Now here if you try to see across this one, now here it is shown that the function is defined in terms of this. Now the point theta, that is the threshold level, is being shown over here. Your activation function shows that if f of x, that is this is the value of x, and if at this particular x, if x is what, that is your net functions. So if x is greater than theta, if x is greater than theta, then the output functions, that is y is equal to f of x, is going to produce 1. Otherwise, if it is less than theta, it is going to 0. That is what, this side is 0, this side is 1. So here the theta represents the threshold value. This function is most widely used for the single layer network to convert the net input to an output. So that's how you can able to you are giving a net input, and that's for a given input, and you will able to decide at which side it will be lying. So this is basically used in a single layer network. That is what. Now going to the next, this is a bipolar network. Now if you look across the bipolar network, here this is a just like a binary network, but the point of f of x is having a value in terms of +1 and -1 instead of 1 and 0. So here it is exactly like binary step functions. The thing is that where you can say that the x, when it is greater than theta, it is going to produce +1, and which is less than theta, it is producing a -1. So this function is also used in the single layer network. So that is how it is being put across. Coming to the sigmoidal functions, the next one, this is a very important and most widely used in the neural network. There are many other function is there. However, for your level of understanding, we will go with what is restricted to certain which is being illustrated here. The sigmoidal functions is basically used for the backpropagation network to reduce the computational training level. So backpropagation is a different area of discussion that we'll discuss in our future course of our discussions, where for the time being you have to understand that this function is basically just like a human brain systems. Here if you try to see that we are representing the value which is having a range between 0 and 1. So that means anything which is 0 and 1 means anything which is less than 0 or anything greater than 0, it is represented in the form of a S-shaped functions. If you see that, it is somehow appears like a S-shaped functions, and each value of S is represented in terms of a lambda. Lambda is nothing but a steepness parameters. So as the lambda changes, the S shape is getting more and more vertically inclined. So here you have to understand that it is different than a linear functions, because of this sigmoidal functions shape, that is a binary sigmoidal function. Binary is 0 and 1, and under the binary sigmoidal, this shape, when we represent this function between x and f of x, it is represented as f of x is equal to 1 upon 1 plus e to the power of minus lambda x exponential functions, where x is the input, summed input, that is what we give all the summed input, and its lambda is nothing but steepness parameters, and that's how we will be able to produce the output. So that is what we define in the range of a sigmoidal function is what? Between 0 to 1, just like a fuzzy egg conditions. Now coming to the bipolar sigmoidal function, it is just like a sigmoidal function, only the difference is that this binary is changed by bipolar. Now here when we try to see bipolar case is that it ranges between -1 to 1. So here the function, when it was 1 by 1 plus e to the power of minus lambda x, under the binary condition, in the bipolar it will become 2 upon 1 plus e to the power of minus lambda x minus 1. So if you further solve it, it will be 1 minus e to the power of minus lambda x by 1 plus e to the power of lambda x. You remember this one, if it is here f of x is equal to 1 upon 1 plus e to the power of minus lambda x. So here in these conditions we are going to produce 1 minus e to the power of minus lambda x by 1 plus e to the power of minus lambda x. So that is how. And if you want to further solve it, you will be getting this one, f of x is equal to lambda by 2 1 plus f of x in a square bracket and further multiply by 1 minus f of x in a square bracket, if you further simplify this one. So this is what we call it as a sigmoidal functions, very important functions. Now we go to the next function, is a ramp functions. Now if you try to see the ramp functions, there are three categories: saturation linear functions, symmetric saturation linear function, and piecewise linear function. Now in the ramp function, ramp is nothing but this is how the ramp is being defined. Now here when we define the ramp functions, here we are having a range which is being given 0 to 1, 0 to 1. So that is 0 is here and 1 is here. Now if you see the 0 to 1 here, what is intermediate portions? It is a slope. So this slope will be having a individual x values, individual x value. That's why it is termed as, if x is greater than this theta, if this 1 is theta is equal to 1, so x is greater than theta, then it is 1. X is less than 0, then it is 0. X is between 0 and theta, that is 0 and 1, it is x. So that is how we define this every value of x. That is the graphical representation. The next is the same things, but it becomes a bipolar, or we can say that symmetric. Symmetric means this is 1 here, then another side it will be -1. That is how. So here also you try to see this one, you will be having a function. So in here it was 0, now it become -1 here. So anything greater than 1, anything less than -1, anything between -1 and 1, that is what we represent in terms of a 1, x and -1. So here it is 0, -1, here it is 1, and this particular case is nothing but every value of x. Between these range, every value of x. Another is that piecewise linear functions. That means we take into considerations not 1 rather than half. So if you can take a half of the intervals, that means we take an interval up to here, from here to here, half. So it is exactly the same way how you represent. Now here one example is being shown for your easy understanding. Normally in this university paper they used to always put this activation function followed by one examples also. So it is for your easy understanding, one example is given. Here input is given 0.8, 0.3, 0.2, 0.6, and x1 is at the x1, x2, x3 node point, and weight is being drawn here in terms of a -0.2, 0.3, 0.8 and 0.5. Bias is given. Bias is normally being put for any almost all the cases is near to 1. So here bias is also 1. So find the output using a binary sigmoidal function and bipolar sigmoidal function. So how will you solve this particular case? The very first thing is that, first of all, what is that? What is y? Y is consisting of a two part. The first is your summing of the input and weight plus bias, that is one part. Second part is the activations. So first part we are doing y is equal to f of net. F of net is nothing f of ym. So that is equal to f of sigma I is equal to 1 to 4 xi wi plus b. So all the value of I is equal to 1 into 0.8 into minus 0.2, 0.3 into 0.3, 0.2 into 0.8, 0.6 into 0.2, like that you add it, then plus 1. Then when you add everything together, and this bias is also having a weight is given 0.25. So 1 and 0.25. So everything is being added. First you have to add everything, then you have to add with this, then that is how you got it as 0.64. Now what is next? We have to apply for the binary sigmoidal function. In the binary sigmoidal functions, what we have discussed here? This is the binary sigmoidal functions, and this is a bipolar sigmoidal functions. So you are putting the value binary sigmoidal functions y is equal to f of ym, that is f of ym. You can put this one as ym. F of ym is equal to 1 upon 1 plus e to the power of minus 0.64. So you put it as, when you solve it, you get it as 0.6548. Now the other part is that bipolar sigmoidal activation function. Bipolar sigmoidal activation function means f of y in. F of y in ym means what? You are putting, you are writing 2 upon 1 plus e to the power of minus 0.64 minus 1. That is equal to 0.35. So you get two different form of activations functions, nonlinear activation functions output. So this how we discuss the point related to the artificial neural network and its activation functions. So with this we conclude here, and we will discuss further in the next video series. Thank you.